An object's momentum is defined as the product of its mass and velocity, and was introduced by the French scientist and philosopher Descartes. The formula is written as P equals mv, where momentum, P, and velocity, v, are vector quantities, and the units for momentum are kilograms times meters per second. In a closed system, which is a system not affected by external forces, momentum, like energy, is conserved. We can apply this to collisions, knowing that when two objects collide, the total momentum before the collision is equal to the total momentum after the collision, or P initial equals P final. Now with that in mind, let's have another look at our earlier collision. Now let's break down what we just saw. Let's say that moving to the right of the camera is the positive x direction and moving to the left is the negative x direction. This would make Xander's velocity before the collision approximately 1 meter per second, and Roan's approximately negative 1 meter per second. Now given that Xander's mass is approximately 150 kilograms, and Roan's mass is approximately 50 kilograms, we can find our momentums. We see that Xander has a momentum of approximately 150 and Roan has a momentum of approximately negative 50. And don't forget, the negative only denotes that Roan is moving in the opposite direction as Xander. Now when the principles of conservation of momentum are applied to the collision, we see that we get a combined momentum of 100, but since the yoga balls are elastic, meaning they do not stick together, this positive momentum transfers to the body furthest right, leaving Xander with no momentum and Roan with a momentum of 100, twice his original momentum. Now because Roan's mass cannot change, his velocity must double to compensate for this increased momentum. This results in Roan being sent back with approximately twice the speed he had before the collision. We can also observe a similar result when Ben and Xander collide, but because Ben has a larger mass than Roan, his change in velocity is smaller. Now let's demonstrate conservation of momentum one last time by colliding a basketball and a tennis ball. Center of mass, also known as center of gravity, is a point representing the average position of the matter in a body or system, and an object behaves as if all of its mass were concentrated at this point. For symmetrical uniform mass distributions, the center of mass lies at the centroid of the system. For one or two-dimensional systems with two masses, the center of mass can be located with this equation. For three-dimensional systems, the center of mass can be located with these equations. And for continuous distribution of masses, this equation is used. But don't worry, in this video we will be focusing on the conceptual elements of center of mass, not mathematical. One property of center of mass is that it is the balance point of an object. Here we can see that the center of mass of the hammer is near the top of the handle on the side with the face of the hammer. Now if we try to balance the hammer at a point other than its center of mass, gravity will take over and lower the object's center of mass. Feel free to try this yourself. Now let's apply this concept to balance a cork on a needle. We see that the mass of the forks lower the system's center of mass so that it's near the tip of the needle, allowing the cork to be balanced. Inertia is the resistance of any physical object to any change in its velocity and is described by Newton's first law. Moment of inertia, or rotational inertia, is the resistance of any physical object to any change in its angular velocity, or, in simpler terms, an object's resistance to rotation. For a single object, its moment of inertia is directly proportional to the product of its mass and the square of the distance from the axis of rotation, which can be written as I equals k mr squared, where the units for moment of inertia are kilograms times meters squared, and k is the inertial constant, which depends on the shape of the body. We will not consider this constant in this video because it does not change the relationship between any variables. Next, we will look at a demonstration of rotational inertia using a rod. In this case, the distance from the axis of rotation is the distance from the end of the rod to its center of mass. As you can see, it is easy to rotate the rod. Now, if we add the weight, we simultaneously increase the mass of our system and decrease the distance from the end of the rod to the center of mass, resulting in minimal changes to rotational inertia. Now, if we add the weight to the other end, we significantly increase the distance from the end of the rod to the center of mass, which significantly increases the rod's rotational inertia. The total rotational inertia for any system with several masses at different distances from the axis of rotation is the sum of the rotational inertia of each mass. We can apply this to a merry-go-round, which is a large rotating disc. If one or multiple masses on this disc move closer to the axis of rotation, which in this case is the center of the merry-go-round, then the rotational inertia of the system will decrease, allowing it to rotate more easily. The opposite effect would be observed if the masses moved further from the center. Now let's watch a demonstration of this.